the flow assisted corrosion in details. We looked at the erosion corrosion of metals. We shall continue that erosion corrosion now, and then we will go on to the cavitation corrosion. In the erosion corrosion, we looked at the importance of erosion corrosion. We also saw how erosion corrosion can be different from the flow assisted corrosion. In the flow assisted corrosion, it is the diffusion of the corrosion product that is the rate determining step. If it diffuses faster, then the flow assisted corrosion rate increases, and so the formation of the film is essentially governed by the dissolution of the metal ions. In the case of iron, it is Fe2 plus majorly and certain amount of Fe3 plus, and then they reform as a magnetic oxide. And the role of flow is to retard the formation of this magnetic oxide, and as the flow is higher, the film becomes thinner, and the film also becomes rough, we can say, to some extent. We saw that the factors that affect the flow assisted corrosion or material. In the case of steel, you add chromium, and it becomes strongly oxide forming chromium, the flow assisted corrosion decreases. And the environment, what are that? The pH is one factor. The other factor is the velocity. Other one is the temperature, okay, that we look at these oxygen content. Okay. More importantly, that the flow assisted corrosion goes through a maximum, and the maximum temperature depend upon whether single phase or the two phase flow, irrespective of the velocity that happens. Velocity increase, of course, the erosion this is flow assisted corrosion increases. So that that's is an interesting thing, that high temperature, they do not really happen. Boilers, they do not happen at all. The increase in oxygen content also lowers the flow assisted corrosion because it facilitates the oxide formation on the surface. So that leads to the what is called as a new water treatment, called as the oxygenated water treatment in some of the boilers. The oxygenated treatment may have some problem that we are not going to discuss now here. The other effect is a mechanical effect and flow and related to that actually, okay, and that depends upon the factor like the velocity, the pressure, and the turbulence that are going to be there. So they are all going to contribute to the flow assisted corrosion, and turbulence means design also plays an important role. In comes the erosion corrosion, we say the damage is really there is an impact and leading to film damage, and there is a film damage, and of course the corrosion production falls. Over year 2, increase in turbulence would increase the erosion corrosion. The erosion corrosion would get accelerated when you have solid particle suspensions actually, and so that is a key issue in the erosion corrosion of metals. We saw the various factors that we listed rather the various factors affecting the erosion corrosion. and they are film formation, the film stability, other is the velocity, and the next was on the materials. We saw the film formation and film stability in terms of film characteristics, right. What are the characteristics we talked about? We talked about the hardness, resilience, porosity, and loss of porosity rather, I think, absence of porosity, density, okay, and the ability of the film to reform, that probably we did not discuss, okay. If the fallen film gets damaged, how quickly the film can reform on the surface. The next aspect that we will be discussing now is on the velocity. One thing that you might look at is, we can generally say that when the velocity increases, erosion, corrosion increases. But we also know that there are other forms of corrosion like pitting corrosion and crevice corrosion. They all drop when you have velocities, right. We have seen when we discussed the pitting corrosion and crevice corrosion topics. It is also necessary to understand that there is a critical velocity above which the damage is becomes significant, right. And this critical velocity that we talk about, it is material dependent, material, and of course the environment dependent. Now, if you want to just have a feel of it, okay, I just give some data here, okay, how the corrosion rate, the erosion corrosion rate will change depending upon the on the materials, okay. Suppose you take say material, let us take copper, Admiralty brass, and you can take let us say C706, and this is copper nickel, right. This is copper tin nickel, right, and you also have C715, because we need to put some zeros here, okay. This is copper, I think 30 nickel. We also have C722, okay, and this consists of some alloying elements, like you may have some iron, maybe some no, not nickel, iron, some titanium, and things like that. If you look at copper, in fact, it's very interesting. Low velocity, right? If it is going to be less than 3 feet per second, all are problem. You know why? You take a pipeline, you take a heat exchanger, when the flow velocity is low, they are not the right material to use. Any idea about it? What do you think? Low velocity is also a problem. See, most of the process fluids might have some kind of particles, second particles, dispersed particles. Sometimes in heat exchangers, if you see water, maybe some foulant, when the velocity is very low, then what happens? They start depositing on the surfaces. It's not erosion corrosion problem, it is another kind of problem that you are going to get, okay. And so you normally have problems in these cases. So you can, if you want to rank it in terms of the properties, I say this is poor. I mean, in terms of the erosion corrosion resistance, I would say this is copper is it's going to be here, okay. And of course, you can also go for stainless steels. Or titanium alloys, okay. So maybe in seawater. See, if you increase the velocity, okay, you would find that stainless steels are good, titanium are good, okay, and this could be I would say moderate levels, okay, and they could be moderate levels and it could be moderate levels, okay. This can be even okay. So these all all these copper based alloys, the velocity is maybe around about, I think probably about you can go up to maybe about 6 to 9 feet per second velocity that you can go for it. This is higher, okay. So beyond that, the copper based alloys would have a problem. So higher velocity means stainless steels and titanium alloys. These are the ways that you can use it. But titanium alloys cannot be used. I mean, titanium alloys can be used, but the stainless steels of all categories cannot be used in seawater application, right? There are some problem. What is the problem there? We use a stainless steel in seawater application. What is the problem? Yeah, it could be pitting corrosion, crevice corrosion. So you can only use a highly alloyed stainless steels like super duplex or hyper duplex stainless steels, or go for super austenitic grade stainless steels. Now if you look at the copper based alloys compared to the stainless steel is much harder when copper based alloys are reasonably softer using before. So the utility of these materials are restricted based on the flow rate applications. If the flow rate is increasing, I think the choices are going to be much limited, okay. You go for stainless steel or titanium based alloys. But the same logic, if you look at a cast iron and steel, so which one do you think will be better from the erosion corrosion point of view? Okay, So, this is better. This is inferior compared to that. Sometimes the velocity can have beneficial effect, right. This they have reported for 347 stainless steels in red fuming nitric acid. They found corrosion rate, it drops like this, maybe within about, let us say 12 feet per second, it drops like this. In the case of aluminum alloy is slightly different. Corrosion rate versus velocity. Something like this. The reason being, in aluminum alloy what happens is, so aluminum alloy that you have, it forms two kinds of films. Aluminum nitrate and the other film is Al2O3 film. They are also nitric acid. Now, aluminum nitrate is a salt film, and if you increase the velocity, the salt film just gets disturbed and goes away. Aluminum oxide is quite intact. So initially the corrosion rate increases because of the removal of aluminum nitrate salt product. After this, what happens? The aluminum oxide remains on the surface, and the subsequent velocity, it does not disturb Al2O3 stable. So the corrosion rate does not change after this. So here, so this means here removal of AlNO3 thrice salt. The mechanism here is different. The mechanism here, stated mechanism is that the corrosion of steel in nitric acid leads to the formation of nitrous acid, and the nitrous acid is corrosive. Okay, it's corrosive. Now what happens? The flow, when there is a flow, what happens now? The nitrous acid is removed from the surface. So subsequent corrosion by nitrous acid is avoided. So increase in velocity decreases the corrosion rate because the accumulation of nitrous acid does not occur because of the flow, the velocity. The next thing that we talk about is the turbulence. Now the turbulence can happen if the surface is not smooth, if there is a change of direction, or if there is reduction in the diameter of the pipeline, can happen. So, higher the turbulence, higher is the erosion corrosion. This is very predominant in the heat exchangers. We have seen the heat exchanger the overall when you discussed, I think, galvanic corrosion, some of you might recollect, right. What is that? If you recollect, so you will have lots of tubes, right, I think. So the liquid enters through the header, right, the shed, and there is almost a 90-degree turn and it enters. The maximum turbulence they occur at the inlet, right, and as it travels towards inside, the degree of turbulence decreases. So the maximum damage in the heat exchanger, it occurs at the inlet, right. So that is why it is called as inlet corrosion. Now how do you really avoid this? One way people avoid is they go for inserts, they are called as ferrules, right. So this is a tube, for example. This is the ferrule, okay, and it is not necessarily, they do not protrude, they just go inside, these things, okay. I just shown it for convenience. Now this ferrule, the advantage of this ferrule is that the ferrule can undergo erosion corrosion. When it gets damaged, you can replace it and put another ferrule. So the life of the heat exchanger significantly increases, okay. But there is still a problem. What is the problem? When the fluid or liquid enters here, there is going to be a small step, this is a small step. So there can be erosion corrosion here. So so you need to smoothen out, you need to make it like a feathery kind of tapering off has to be done in order to reduce this erosion corrosion, okay. But use of ferrules are being done, so it is industrially accepted practice to minimize the inlet corrosion of heat exchangers. impingement is there. Okay, impingement is a direct impact. So the impact can be high here. Huh? So more erosion, corrosion can take place. This is impingement attack. Huh? Where impact takes place, and if you are going to have solid particles, then the extent of impingement attack becomes quite significant. And these are common, it can happen in gas turbines, okay. It can happen in cyclones, it can happen actually, right. So some of the units they really feel you know, in gas turbines where do they happen? It can happen in the turbine blades, right. It can happen in aircrafts, external part, it you know, it moves at a very high velocity, it can happen. Some cases you can change the design and you can improve upon, but there are cases where you can't change the design everywhere, right, but where there is a possible we can change the design. For example, here you do not make it, you know, you increase the, one way to do is that increase this radius. When you increase the radius, what happens now? You will have less impact, less turbulence can occur. The other way, of course, to visualize this is that you take this part little heavier, right, you make it as thicker, where you know for sure that you are going to have impingement taking place. See, it can happen in heat exchangers, you know, you in heat exchangers you have baffles, you know, sometimes they hit, right. So it is possible that you can increase the thickness of that, you know, more, so that life of the overall component can be increased significantly. So when you look at this, one thing becomes clear, that the design plays a very important role in minimizing the erosion corrosion, right. When I say design, all that reduces the impact, impingement, all that reduces the turbulence can increase the erosion corrosion resistance of the system. So it's a design parameter as much as material parameter, as well as the environmental conditions that are operating in a given system. Let us go to materials. What should be the material property you think that would give you a better erosion corrosion resistance? Should be hard. So it should be a from mechanical properties point of view, it has to be hard. Yeah, it is sufficient to have only hard thing. What else? Huh? Yeah, abrasion resistance comes from hardness. I mean, you increase the hardness, generally they are resistant to that. Is it sufficient to be just hard? Yeah. So you should be also having corrosion resistance. Of course, that is involved in the corrosion resistance package, right? So in corrosion resistance, how can you improve the corrosion resistance? Either the material can be noble material, or it can be passivating material. These are the criteria, right. Let me give an example. Martensitic steel. I have given some 4 examples here. I can give, if you want, I can give you even aluminum. I can give you even lead if you want. Now let us take for simplicity only the stainless steel family. Can you just compare and what will be your view about just erosion damage resistance and corrosion resistance damage? Please listen to my question. You have 4 different type of steel. You can have 2 types of damage mechanism. One is erosion, other is a erosion corrosion. So what will be in your view? Suppose I take for example simply erosion, right? How do you rank this one? Okay, no, but yeah, you are right. Then okay. So when it comes to erosion, of course, assuming that the hardness is same. I mean, I am not really going to vary too many things, right? Assume that the hardness of martensitic steel and stainless steel are going to be the same. Okay. So if you look at erosion, both martensitic steel and martensitic stainless steel will be almost the same. When it comes to erosion corrosion, martensitic stainless steel will be better compared to martensitic steel. In fact, it might so happen the ferritic stainless steel may be better than even martensitic steel, depending upon the corrosive nature of the environment. If the environment is very corrosive, it is possible that the erosion corrosion resistance of a ferritic stainless steel could be better than erosion corrosion resistance of a martensitic steel. Why? Because martensitic steel generally are more prone to corrosion compared to a ferritic steel here. But the most vulnerable among all this, from the erosion point of view, which is the most vulnerable here? 1, 2, 3, 4. Ferritic will be more, right? Next better will be ferritic stainless steel. Of course, martensitic steel and martensitic stainless steel will be almost similar. So I wanted to understand, okay, the concept of alloy development, how it's been done. Aluminum and lead, of course, if there are low velocities and we have less problems, when velocity is increased, then it's a problem. See, this is a very interesting thing. It is not necessary that you can extrapolate at all velocity. At a normal velocity, it is possible that the lead for example in sulfuric acid, dilute sulfuric acid at static conditions, at very low flow conditions, lead may be good. Okay. Whereas with a high velocity, the lead is softer, so that fellow will not even withstand that actually. So it is not possible to extrapolate, at given velocities to higher, because at higher velocities the mechanism of damage may be different. Is more mechanical damage dominated corrosion problems than the corrosion dominated problems. At low velocities, what is the dominating mechanism? Low velocities is corrosion. At higher velocities, the dominating mechanism will be mechanical factor actually. So it is not possible to just make extrapolations the way you want it actually, okay. I would like to give an example of how these things really happen in practice. There's one of the industries in India was making what is called as hydrogen generation unit. It was they had a license. It is able to have engineering capacity. This unit was, I think, commissioned somewhere in the Eastern Europe. The hydrogen was generated from hydrocarbon. When it generated from the hydrocarbon, it consisted of hydrogen plus water. Of course, there will be some amount of carbon dioxide, some amount of formic acid or kind of stuffs, but these are very low quantities. If I want to give hydrogen to the user, what I should do? I should strip the hydrogen from water, carbon dioxide and formic acid. The carbon dioxide and formic acid, they dissolve in water. So when you remove water, automatically this go away, right? How do I remove water from the gas? Yeah, you heat it. You think gas will remain there? How do you do that? You are talking about industrial unit. They are going to produce a few tons of hydrogen, right? You can't use chemicals and all kind of stuff. Any other method you can do? No, simple. Huh? Yeah, first of all, you pressurize. Not sufficient. Lower the temperatures. You pressurize and lower the temperature, what happens to water? Water will condense, right? The water condenses. And the air will be free from, a gas will be free from water. So that's what done people do in the industries. Now, when you pressurize it, you lower the temperature, the water is getting separated. This is a good water. Huh? So this is now pumped. And they call this as process condensate in the industry. It's a nice water, no chlorides and all, but what does it have? What does it have? It has carbon dioxide, it has got formic acid, it's a pure water, it's almost like distilled water. So what do you think is property? What will be its pH you think? It will be alkaline, neutral, or what do you think? Yeah? So it should be slightly acidic. Right? Now the whole line is under a higher pressure, right? So you compress it, you pump, and then so there is a pump here, it's a pump. So there is a compressor here. Okay. So this is called as a pump, okay, say condensate pump. And this water is pumped to, you can pump it to a water treatment unit and then to boiler, you can do that, okay. Now the interest comes over here, this is the pump. In the pump, the fluid goes at a very high velocity, right. So what are the process parameters? These are some of the process parameters, right. you can see that the flow rate is 15 meter cube per hour, and linear velocity is what matters for us. It is about 2.1 meters per second, that is the velocity the water goes, and other parameters like suction pressure and discharge pressure are given. From the point of view of corrosion, these are interesting. Now impurities of carbon dioxide, formic acid, all the stuffs. So the pH is between 5 to 6. The temperature is between 30 degrees Celsius, and maximum of course you can go to 40 degrees Celsius atmospheric temperatures. So they initially thought that in the design, they thought that the pump should be made up of martensitic grade stainless steel. They were planning to have martensitic grade stainless steel, but somewhere something happened. Finally, when they just about to start the unit, they found there is a typo problem. Instead of martensitic stainless steel, they went for martensitic steel. Okay. So they realized just one day before that this is the problem. Now the whole unit, hydrocarbon unit, is a part of the refinery system. You cannot stop this. If you stop it, everything will be stopped, and they start running the system now. The good point was they were having standby pump, because these are the units that can go bad, and so they do not want the system to be shut down, unplanned shutdown. So they had a standby pump. Then they thought, okay, they probably knew that martensitic steel is not same as martensitic stainless steel. Then they started operating one pump for about 3 hours, then moved to another one for another 3 hours. They keep on shuttling between these two things actually happening at all. So they were a little worried. So why they were worried was that if you want to order another one, it will take another 9 months. It is just not possible. It is not just off the shelf. It takes about 9 months to get the new one actually. Okay. This is about 27. Its slide is 9, right? Okay. So look at this comparison of these materials now between the martensitic grade ASTM A216 grade is a martensitic steel, and ASTM A743, it is martensitic grade, I think, stainless steels. The chromium is between 8.5 and 14%. The nickel is about 3.5 to 4.5%. Okay, molybdenum is in this range now. Now they are worried because martensitic steel is really corrosive even compared to carbon steels actually. Okay, so what will happen? So they started working alternatively, and then they called one day and they said, well, there is a problem. It was indeed a problem. The issue here was different. Suppose you have pump 1 and pump 2, one pump operates, other pump is standby. When you keep a standby, if this environment, the pH about 5 is there stored, the corrosion is not going to stop. Only erosion corrosion of course is reduced because there is no flow, but corrosion will not be stopping, right. So it is not prudent to keep the corrosive liquid getting stored. They might think that there is no erosion corrosion, but there is a corrosion at all, right. So one of the things that they can at least look at is monitor the thickness of the pump and see what happens. So one thing you can do that, right. Other thing that you can do is that do not start alternatively, at least start one for 1 week and keep the other one dry, so that the flow does not corrode at all, right. Otherwise what happens, you are simply corroding both of them, and it is not really happening. So what was done was they advised that okay, please do not start alternatively, at least keep for about a week time and keep the other one dry happen. So then what happens, then subsequently what we do is then we can make a calculations actually, okay. You can make a calculation because you know what is the normal pH and all. Of course, it is very difficult to make exact calculation, we can make some kind of comparison for this particular pH what is expected to happen at all. It so happened I mean the pump was safe for 6 months by the time they can get another unit. The point I want to emphasize here is that it looks simple between the modern static steel and modern static stainless steel, but a small error can land into a problem and can lead to unexpected failure, can happen at all. So that is something you do see happening in industry. This is not very old, this is probably about 2 years, yeah, about 2 years back this incident happened, and it was one multinational company. It is not that it is some spurious company dealing with this system at all. So the point that we need to be looking at is look at the corrosion plus the mechanical, the hardness properties are both are important. This is the passive current. If I damage here, current will rise, it can go like that or it can go like this. Alloy 1, this is going to be your alloy 2, which is better, alloy 2 is better. So the alloy development program will take care of both the electrochemical and the metallurgical aspect of corrosion, okay, so that we do not have erosion corrosion problems. So let us give an example now. Now you have iron chromium, nickel chromium alloy. Let us take an example here. Assuming that the hardness properties are same, which of the two will have better erosion corrosion resistance? You got my question? I am not giving other elements present here, I am just giving the base alloy is iron based, it is nickel based, I have chromium here and chromium here. Assuming that the hardness is same, which of these two will have better erosion corrosion resistance and why? What do you think? Certainly one will be better than other one, do not you think so? So what do you think?
Chromium.
Yeah, nickel chromium. Maybe you guessed it right, or you figured out the science of it. Okay, so let us look at the science of it. Why do you think nickel chromium is better than iron chromium? Yeah. So relatively nickel is more noble compared to iron. It is as simple as that. Okay, so you find that this is certainly is better. So those cast irons which are having more nickel, okay, or will be better than the one with nickel free cast irons. Okay. So broadly that you can say the same is true in this case also, right? You take copper, zinc and copper nickel, right? This will be better. Now if you are going to add, let us say, copper, zinc and aluminum, suppose add to this. So this is better than copper zinc. Now if you take, let us take the case of alpha brass and alpha plus beta brass. Which one do you think will be better in terms of erosion corrosion damage? Yeah,
Alpha plus beta brass.
alpha beta will be better. So this is where you have to look at. So I mean, alpha beta brass, as you metallurgy guys should know, right? It's a two phase one, right? The two phase will have a better toughness, better hardness compared to that actually, right? So if you look at here, it's a very interesting thing that can happen. The limited extent, de-alloying, erosion, corrosion resistance. No, I don't call it resistance here, I say erosion, corrosion, both scales are going same manner, okay. Can you plot how this will happen? So as far as de-alloying is concerned, this guy will go like that, corresponds to this, right. So what will happen for erosion, corrosion? Something like it will go, right. Now depending upon which is the dominant mechanism, right, if there is no flow, very low velocities, probably you choose alloys of this here, right. But if high velocities you try to choose alloys somewhere here. Otherwise instead of de-alloying they will fail by erosion, corrosion damage. The other example is iron silicon. Actually you are going to have 14.5 weight% silicon. It's excellent material for handling sulfuric acid, especially used for impellers. You can't use for a pipeline there, right? Can you use it for a pipeline? Iron, silicon, alloy of this one. Can you? Can you make a pipe out of this? You cannot. It's only a cast product. It's so brittle. You can't make. So it's okay for the impeller. Pump, you can do that, no problem. Pump also you can, no problem. Okay. So the silicon forms a very hard silicon dioxide, protective oxide, hard oxide. So it's certainly better. You can also give an example, let us say duramate is an alloy, duramate 20 it's made only for the sulfuric acid applications actually. It consists of 30 nickel, 20 chromium, 3.5 copper and 2 moly. Take this versus a stainless steel like let us say type 316 stainless steel. This is 8 nickel, 18 chromium, actually it is not 8 nickel, it says 10 nickel actually, okay. 10 nickel and you have about 2 moly. Duramate is far better from the erosion, corrosion resistance point of view. You can use nitric acid, you can use it in the seawater applications or going to be there actually. So it is a combination of the hardness plus this is what required in order to have better erosion, corrosion resistance. That is the point we try to drive home in the discussion. Okay. So, we have almost come to the end of the discussion related to erosion, corrosion, and having understood the mechanism, understood the factors affecting the erosion, corrosion, you should be able to tell how we can prevent or you can control erosion, corrosion. Yeah, can you just, what are the ways that you can do that?
Material selection.
One is the material. Select a better material that has good erosion corrosion resistance, that you know how it comes out. It comes out from the hardness plus the corrosion resistance properties. Okay. Then what is the other important thing?
Structure, the turns, the design.
The design is second most important thing. You can have a design to avoid turbulence. You may not avoid completely, but you can minimize it actually. Okay. All this involves, like, you talked about radius. Okay, radius of bends to be increased and never 90 degrees. That will give big impact. In fact, people talk about 20 to 30 degree is what is the radius. I mean, is the angle between the turn you can talk about. Okay. What else we can look at?
Filters, maybe we can use.
Yes, you can use some filters. Even in the design, also you can talk about using what you can use. You can use extra like baffles. You can use, okay, to see that it's not going to impact directly, right? Again, how do see? This is not okay. Okay, right? So you see that the fluid. So the branching, the way how we want to make the branches. There are only examples. They are not exhaustive by itself. Look at over design. Place over design where the critical parts. We talked about the ferrules, heat exchangers. So wherever the other way of looking at it is this, it is going to damage, impinge, it should be readily replaceable. You can able to replace it right quickly. So that's also is acceptable. Yeah, you were talking about something. Yeah, what is the other alternative thing?
Use of filters to remove solids.
Yes, use the filters to remove solids. You can also talk about altering the environment, right? pH control, inhibitors, all these stuffs you can do that. You can talk about hard coatings. You can look at the time tested one, what is called cathode protection where possible. But not of course everywhere you can apply all these methods and where possible. But what is the bottom line? The bottom line is the bring down the cost, right, and the bottom line is safety, where safety is involved, right. So, so these are the few available methods to control the erosion, corrosion. If you want, we can discuss more on this later. Let me just finish up this cavitation damage, and I know this we are already spent about close to 1 hour 20 minutes, right, I think. Let us cover this topic of cavitation damage. Now, you know what a cavitation is. What is this? There are several persons with a mechanical engineering background, right? You should say quickly. What is cavitation damage?
So in cavitation, the pressure is different at different stages, and this causes bubbles. As pressure changes, these bubbles can implode. When they implode, it can damage the surface layers of the turbine or the blades and other equipments.
Is very correct. Okay. So, the cavitation damage essentially happens because of implosion right, implosion of bubbles on the surface of the structure. And this transfers huge amount of energy onto the structures. This happens, as you said, in impellers, in propellers, in turbines. Turbines also you compress, right? You compress it, okay, it happens. So, understand how these things can happen in a in an impeller, okay. You can consider a situation. I am just giving a brief account given in the front of the book. I will not go much details actually. Okay, you can consider a cylinder having water, right. Sorry. So, it is in contact with a tight piston, right. So, you have water and I have tight piston. When you move this piston up, what happens? The pressure reduces, right. Now, we know that the water can be boiled even at ambient temperature by lowering the pressures. So, it is possible that we can boil the water at ambient temperature if you are going to lower the pressure. So, as you lower the, as you raise it up, it lowers the pressure here, then what happens now? Water evaporates. When again you reverse this, direction, then there is going to be compression, then lead to condensation. The bubble will start shrinking, but beyond certain level it can't shrink, then what happens? Then it is going to be implosion. It implodes. When it implodes, then it's a shock, right? It exerts a pressure as much as 60,000 pound per, let's 60 psi, something like that you can say. And this pressure exerted can lead to plastic deformation. How can you verify there is a plastic deformation or not? Yeah, shape fine, but see the small bubble, it won't change the shape so much. Huh? It could be a dent, yeah, it could happen, but dent can happen, and you could simply corrosion also can have a dip. But with the plastic deformation, how can you do it? Metallurgists should tell. What do you see? You will see a slip step. If you are going to look at this in the microscope and you see nice deformed layers, right? You see slip steps. That's indication of the plastic deformation of metal. To summarize that, to cavitation to occur, it must have a region of low pressure where the liquid will evaporate, and then the evaporated vapor will be subjected to a higher pressure. The pressure is sufficient enough to condense and lead to implosion, and that leads to the plastic deformation of the material. If you look at the mechanistic point of view, we want to draw some kind of schematic diagram of what happens in the material. All the metals are covered with some oxides, right? Like this, it form a bubble here. When you increase the pressure, what happens? The bubble implodes, this gets damaged. When the area is getting damaged, then it gets corroded again, right? Now what happens? It is very interesting now. The formation of the bubble over here is much easier, right? Because it gives you additional surface. So the bubble can go and rest on this. Then what happens? Then again implosion, film damage. Then what happens? Then there is going to be again corrosion, film formation. Then again starts, right? Again bubble will come and form on surfaces, so starts continuing process. So, the pit grows primarily because the surface becomes rougher, it becomes easier for the bubble to sit on the surface. Please notice that the very implosion by itself is not a problem. If it happens within the liquid, I have no problem. It happens only on the surface, it causes the damage. So, the cavitation damage that is occurring here, more of a mechanical damage, and corrosion is a consequence of the removal of the film, exposure of the bare metal to that, and again the further damage comes by a mechanical process, implosion of the bubbles. Of course, corrosion occurs. Why? Because the environment interacts and then forms a film and so on and so forth. Now, this also there are of course several examples it can happen. This also depends on the design. Suppose I have a pipeline like this, they want to join onto this pipe, actually they reduced like this. Now look at this design here, is a pipe, the larger diameter, smaller diameter, you weld it like this. Where do you think the cavitation damage will occur? Yeah, just at the reduction area, this is the reduction area, right? Because the pressure is increasing. So such kind of design mistakes you should be avoiding. The impeller you can't do anything, right? The impeller works on that principle only. There is a suction, the pressure is increasing, you can't do anything, but these designs are, you can be avoiding it actually. I talk to many people who do this, but surely this is the place where you have problems for sure. So how do I control of this? One of course is hard materials, coatings, of stellite coating, copper containing coatings, you can do that. You can also have resilient coating. See, the resilient coating, what does it do? It just does not lead to plastic deformation, right? And you can also have, it also means like rubber lining, for example, you can do that. You can have smooth surface. What is the advantage of smooth surface? It does not allow the bubble to stick on the surface. You can use inhibitors. The fact that inhibitors reduce cavitation damage means there is a corrosion taking place, simply not a mechanical damage per se. Okay, so that should come to the end of discussion.